Still preparing?
Yeah. OK. Looks like it's working now. All right. So I'm going to talk about Schottky groups and maximal representations. And this is all joint work with Nikolaus Tribe, who's at the University of Heidelberg. We put this up on the archive like a couple weeks ago if you want to read more, if I made you curious enough. So first, I'm going to tell you about the motivating examples. So those are Fuchsian Schottky groups. Oops. OK, so definition. Fuchsian Schottky group. Is a discrete subgroup gamma of PSL to R, defined way better by a picture than by trying to formalize it with indices everywhere. So defined in the following way. So you take your favorite model of the hyperbolic plane. I'll do it on the disk. And then you pick some even number of disjoint half spaces. And by a half space, I mean take a geodesic, so something perpendicular to the boundary at both ends, and then take one of the two halves so that it splits the hyperbolic plane in two. So I want bunch of disjoint half planes. So let's do 4. But I could do 6, 8, any number, at least 4.
Is there a reason that some of them are colored differently than others?
Yes, I'm coming to that. So I chose 4 disjoint half planes, and then I drew 2 arrows. And I'm going to tell you what the arrows mean. This picture is always slightly misleading, but then I'll write something to make it better. So A and B are going to be generators for my subgroup. And so there will be generators A1 up to AG map the complement of a closed half space or half plane to the interior of another one. So what do I mean by this? So it means that when I draw this A with this arrow and those 2 half planes, what I mean is that whenever I apply A to if I apply A to the complement of this half plane, so everything outside of this one that's at the tail of the arrow, so everything but that gets mapped into here. So you want to imagine that A takes this geodesic, stretches it out, and glues it to this one that way, and sends everything inside. So once you do that, right? So I'll make a picture of what happens when you do that. And the colors will help again. So if I do this, and I said everything which is not in here gets mapped into here. So that means these 2 blue things are not in here. So they get mapped somewhere here. So I'll draw them like this. And this red thing itself actually is not in here, so it gets mapped somewhere here as well. Right? So you have a copy of basically like this is a half plane, everything but that. And this is also a half plane. And so this map identifies those 2. Make sense? And same for the other one.
And A and B are elements in SL2 or PSL2.
Yeah. So A and B should be or the generators should be in PSL2R. So they're isometries of the hyperbolic plane.
You're thinking of it like as Mobius transformations on the upper half plane or something.
Yeah, you can think of them as Mobius transformations where this is any disk inside CP1. So I mean, more generally, Schottky groups identify disks with disks, or yeah. But I want to really only think of those that preserve a hyperbolic plane. Okay. So under these hypotheses, you can show that gamma is free on its generators. So there are no relations in this group. It's just a free non-abelian group on A1 up to AG. And then also, you can take the quotient of the hyperbolic plane by this subgroup, because it's discrete, free, very nice, is surface with non-empty boundary and it inherits a hyperbolic metric.
Is it actually a boundary or a punctured surface?
Could be either. So the way I wrote it like this, it's with boundary. I mean, it's the interior of a compact surface with boundary.
That's
yeah.
right, okay.
So I guess that's what you mean with punctures. Yeah, it's the same.
Right. Because otherwise you have to worry about collar neighborhoods and what you mean by hyperbolic metric.
Right. I want complete metrics on.
Yeah.
Yeah.
So that's, so okay.
I could say punctured. Yeah. But somehow I like to think that this is the boundary, even though it's at infinity. So.
Sure.
Depends how you think of your compactifications, like whether you cut or add infinity actually at infinity. Okay, so you just imagine taking the region which is outside of all the half planes, so this middle part which isn't colored, and then you see that the edges on the sides of it get identified together. And with a little bit of imagination, you can see that this, when you quotient out by these two maps, becomes a three-hole sphere.
So does the gamma is acting freely as well, or?
So gamma is acting, yeah, freely, properly, discontinuously, everything you want. And this is a fundamental region for the action. So you can just look at this X shape, identify the boundary pieces together, and you get that. And the topology of H2 mod gamma depends only on the combinatorics of the configuration.
You mean your choice of these half?
Yeah, so I'll explain what I mean. Here's an example. So you have the choice of half planes, but you also have the choice of your identifications. So this, as a quotient, gives something like this. Or you can think of it as punctures. It's up to you. And if you take the same half planes, but identify opposite ones instead of adjacent ones, then you can convince yourself that the quotient is a torus with one hole. So the number of generators will be related to the fundamental group of the surface, but many surfaces with boundary have the same fundamental group. So you'll have to change the combinatorics in order to get all the possible surfaces. But given the combinatorics, if you just wiggle a little bit the half planes, you get the same surface. That's pretty clear. In order to get a different surface, you have to break something, like change the way they're combinatorially identified.
Is every surface a Schottky surface?
Yep.
Every surface definitely has a hyperbolic metric.
Right. But so I can say more actually. So normally in like classical Fuchsian Schottky groups, you require these half-planes to be genuinely disjoint, like even at infinity. So normally, this is not allowed. Or like maybe this, even, right? So if you allow asymptotic half-planes, so half-planes which touch at infinity, but the open half-planes are still disjoint. So actually, like the argument to show that it's free and acts properly discontinuously on the interior still works exactly the same way. But this is not called like a classical Schottky group. But I want to allow this. So if you allow this, then any hyperbolic metric on the interior of an oriented, compact surface with non-empty boundary arises from this construction.
All of them?
Yep, all of them.
In this surface with non-empty boundaries.
Yeah.
Okay,
So not every surface, not closed surfaces. But as long as the boundary is non-empty, as long as you have at least one puncture, then the fundamental group is free. And so you can construct, in some way, find half-planes associated with your metric, and the quotient will be the right surface with the right metric. So in some sense, this construction is enough to get, like, to describe all of the hyperbolic metrics on any surface with non-empty boundary. If you allow this puncture thing, like where, so I mean, the way you would draw this surface as opposed to here would maybe be this, because like from the point of view of the hyperbolic geometry of the surface, the area should be finite. So in this case, you get a finite area thing, but in this case, you get an infinite area thing. Okay. All right, I think this is all I had to say about the motivational examples. Any questions so far? Okay. So section 2. Want to do maximal representations. So I should go in the order of my title, right? First talk about Schottky groups, then talk about maximal representations.
But then you're only 2 sections?
No, there's 4, but maybe it should be ... Okay. So now I'm going to start with the surface instead of starting with the group and the hyperbolic plane. So let sigma be a fixed oriented compact surface with non-empty boundary. Now we consider Sean's favorite object.
Not sure what that is.
The character variety.
Oh, yeah. Speaking of that, like, is in the free group case here?
Yeah.
The Schottky metrics? Are the metrics coming from the Schottky construction?
Yeah.
Like, what's the type Euler says? Is it an open cell, like the usual situation with like the closed surfaces? Like the type Euler space for a closed surface, like a G, it has to be G2 and above. Right? They're all, topologically, the moduli spaces are all balls.
Yeah.
Like what are?
I think they're all balls again. Yeah.
Okay. Are they? I mean, I just don't remember.
I think that's true.
What the story is.
So, I mean, you want to think of, I guess, Fenchel-Nielsen coordinates, right? Because those work also for surfaces with boundary. You just have a length for each boundary component, and you choose a Pence decomposition, and then you have a bunch of parameters, but they're all either angles or lengths. So.
Oh, I see. So the point is that the proof that it's a ball to begin with breaks it down into a pair of pants, which is in this situation, and then the question is you just have to twist
Yeah, I mean, for a pair of pants, you have 3 parameters, and they're just the 3 lengths, so it's R3.
So yeah, exactly.
Right. But there you can have 0 length on the boundary. So it's maybe not an open ball.
Okay.
Right?
Anyway, I just don't remember.
Because you want to allow this to happen, and this is on the boundary of like the space of surfaces within the space of representations. But yeah. Anyway.
Okay. So it's not okay. So you're saying it's not necessarily an open cell, so it's something different.
I think it can be, yeah. Well, no, it's fine. This the case where you allow 0 is just 0, 0, 0 in R3, and then you can have any other 3 lengths, non-zero.
Oh, so it's an interior point, not a boundary point.
No, it is no, you can't have negatives. So it is a boundary point. Yeah, it's like an octant for the.
Yeah, it's not R3. I mean, that's the R points of the character variety.
Right.
The SLC
Right.
Character, but they're not the same as the.
Yeah.
Not every representation gives you a metric.
Yeah.
Every metric gives you a representation.
So I'm going to tell you actually exactly which representations give you a metric.
Yeah, and that's what I'm asking about actually.
Yeah. So this is answered by this.
Is the Fricka space or the Mueller space like all this open ball is a closed surface? I mean, an open surface space.
So.
Bill's worked this stuff out, like in some
Yeah.
cases.
Yeah.
I just don't remember the answers.
Okay, so Sean's favorite object, character variety. This is a set of representations. So the points in here are maps from the fundamental group of the surface that I define here. By the way, in this case, this means that the fundamental group of the surface is a free group. Yeah. And the number of generators for the free group only depends on the Euler characteristic of the surface. So it's the set of representations, and you mod out by this equivalence relation that 2 representations are the same if you can get one from the other by globally conjugating by something in PSL2R. And this means that the two representations sort of, if they happen to be related with hyperbolic metrics in this way, if they're conjugate, then they give the same hyperbolic metric. This is why we care about this. But there's more. There's like representations in here that don't give you nice quotients. So there's an invariant. Called the Euler number.
Well, I guess there is a space associated with each representation. Just let it act on the hyperbolic plane of the quotient. Like the image of row?
Yeah. It might be horrible. I mean, this could be like, yeah, if it's the identity everywhere, well, then it's not so bad, I guess. Yeah. But I mean, with respect, it doesn't have, it's very far from having the fundamental group of the surface you started with as its fundamental group. That's the big problem. Yeah. Okay, so. Well, it's not free. Every point is fixed. It's maximally non-free.
No, actually it's free because everything's fixed by, you allow everything's fixed by identity in general. So you always say except for the identity.
Okay. But but it's not the identity in the first group. So the see what? Yeah.
Pi 1. Okay.
Yeah. Then.
Yeah, then
Okay. So there's an invariant, and by invariant I just mean a function on this set, right? Which is called the Euler number. Not going to tell you how to define it. It's like cohomology stuff. And so there's a theorem called the Milnor-Wood inequality, which dates back to like 50s or something. And this tells you that this Euler number in absolute value is bounded above by minus the Euler characteristic of the surface. By the way, I should have said Euler characteristic of the surface is negative.
What's the Euler number of rho mean?
So yeah, I don't want to define what the Euler number is. I'm just telling you it's a function on this set. So
Conjugate variant.
E goes from character variety PSL2R into R. It's some function. It's a continuous function.
Defined on the whole character value? Not just yeah, I guess
Yeah,
it is.
yeah, it's defined everywhere.
Right.
It's a representation thing. Like you pull back the Euler class, which is like a cohomology class here, and then you do something with the relative fundamental class because you don't.
Every representation will correspond to a flat bundle. Isn't there a way to like
Yeah,
define it?
yeah. There's a it's an invariant of the flat bundle.
The connection on the flat bundle.
Yeah.
Yeah. Okay. That's how.
But it's not. The definition is not going to be very important for what I want to say. Okay, so it's bounded. Now the important theorem.
It's like an integral formula for it. Like you integrate the connection or something, like put on the flat bundle corresponding to it. That's why it's conjugate invariant. Because conjugation just changes the base when it's defining the bundle. What did you say?
Oh, I mean, because maybe I'm one tricky thing. Oh, yeah, it's because the equivalence of you have equivalence of categories between vector bundles with flat connection and representation with them. The action on one side is
a category. There actually is a categorical connection.
Okay. One thing that I want to point out is that this Euler number is a function on the character variety of like the free group into PSL2R, but it depends on not only the group but also the surface. And I'm going to like pictorially describe what I mean for this. So if this is the character variety of some free group, like let's say maybe the free group on two generators into PSL2R.
Bundles over the underlying surface.
So if this is the character variety, then okay, there's a continuous function from here into this closed interval, which goes from like minus Euler characteristic of sigma up to plus, from Euler characteristic of sigma to minus Euler characteristic of sigma since it's negative. So it's a continuous function on here, and it can take every possible value. So look at the set where it's equal to minus the Euler characteristic of sigma. This gives you some connected subblob. So this is where E of rho equals minus Euler characteristic. But this maybe is for sigma 3-hold sphere. And what I want to say and really emphasize is that this number depends on the initial surface, not only on the group. So in this overall character variety of the free group of rank 2, there is a spot which is maximal with respect to the 3-hold sphere, and another spot somewhere else, actually completely disjoint, which is when this invariant is maximal for the 1-hold torus.
Oh, so as long as you're you're identifying two of the character varieties when they have isometric fundamental groups.
The character variety definition only depends on the group, right? It doesn't have anything to do with the surface a priori.
Sure.
But the function here depends on the surface. So maybe I should call it like E sigma or something, right?
Once you've chosen like what surface you're dealing with, then you're picking out a closed subvariety.
Yeah.
Well,
Open or no, closed. Yeah, it should be closed, right? Is the pre-image of a point. Yeah.
It's just a final product.
Strictly speaking, the character variety in this case is not really a variety.
Oh, is it not? Well, I don't really care whether it's. Yeah.
If you over C, you get an honest variety out of this. But if you replace the quotient, you specify the GIG. Otherwise, it's not even house door. It's not even T1. It's really bad for the computation. The point is, when you restrict the discrete faithful representations, like all of those will be closed points in the DIQ quotient, so you won't actually care. So these like little blobs he's drawing are actually in the smooth strata, essentially, of the character variety.
OK, so where am I going with this? So I started by talking about Schottky groups, and then I said that every hyperbolic metric arises in this way. Now I'm talking about representations of free groups. Well, clearly you can get representations of free groups by doing this construction. When I choose these A and Bs, I can map my two generators of the free group to A and to B and get a representation. And I said here that there's some invariant which depends on a surface and tells me exactly which representations will correspond to the geometric ones. So I know that every representation which is maximal corresponds to a holonomy. And so since it corresponds to a holonomy, it has a Schottky presentation. And conversely, if I present to you a hyperbolic metric this way, I get a representation, and the representation will be maximal by this theorem. And now the point will be to define other Schottky groups in a more general context where maximal also makes sense.
All Schottky groups are maximal, is what you're saying.
Yeah. Even those that have punctures.
In this conversely.
Yeah, and conversely. The only thing you have to be careful about is that the Schottky presentation is like really far from being unique given a representation. Like you can pick a bunch of different presentations that for the same group.
So for open surfaces, every hyperbolic metric is a maximal one.
For closed surfaces also. Maximality of the Euler number always corresponds to being a holonomy of a hyperbolic structure for both the closed surface and
really?
Yeah.
Okay. So these are this is like the generalization of the hitching component or something.
Well, this is only for PSL2R so far.
Yeah, it is the hitching component.
Yeah.
In this case. Like,
Yeah, but it's not a component for surfaces. Yeah, that's the weird thing.
yeah, because the whole moduli is
Yeah.
connected.
Yeah. So for closed surfaces, the moduli space is not connected.
Uh-huh.
And actually, the Euler number takes values into integers, integers between this and minus this.
Yeah.
And there it exactly classifies the components. So that's the difference in like the qualitative, the qualitative difference between the free group and
Cutting out subspaces of a connected thing, but the disjoint subspaces.
yeah. OK.
Is that always the case? For like, so you take a free group, right?
Yes.
And then there's like a whole bunch of like surfaces that correspond to that free group.
Yeah.
And in this case, there's two. But as you increase the rank of the free group, you get more and more and more surfaces.
Yeah.
Right? Like, is it always the case
That the
these
maximal
little
things
blocks
are all
always
disjoint?
disjoint for
I am not sure. I should probably know this, but I don't. Maybe I'll check and tell you.
The next one, I guess, would be the four-hole sphere, right? Then you have the four-hole sphere.
Yeah. And I mean, you can add a hole to everything and add the genus 2 surface with one hole.
Yeah.
Oh, no. That's too higher.
You
Yeah.
get them all. Yeah, you have to go next. Yeah.
Yeah.
You get them all by starting off with the n-hole sphere and just iteratively combine pairs of boundaries. And that if you just do that from like one at a time all the way till you run out of boundaries, you get like all the surfaces with the same Euler number.
OK, so there is a generalization of the Euler number called the Toledo invariant, which is a function now on the character variety for G, any Lie group of a Hermitian type. I'm going to tell you a bunch of examples so you don't have to know and I don't have to tell you what Hermitian type is. For example, G can be sp2nr, and actually most of the rest of the talk is going to be about sp2nr. So symplectic groups, unitary groups, special unitary groups with split signature, special orthogonal groups where one of the P and Q is 2, and a bunch of other ones. There's many of them. They're isometry groups of Hermitian symmetric spaces. You know what a symmetric space is? If it has a Hermitian structure on top of its Riemannian metric, you take the isometry group, it's going to be one of those, and more.
The SU11 case is like what you drew there.
Yeah, exactly. PSL2R is SU11. Yep.
Yeah. Oh, well.
Uh,
Yeah.
Locally.
You drew the model for SU11, but didn't
Oh.
have the group for the upper half plane.
Yeah. I like my real numbers. And SU11 sort of.
Like the
I can write the action of PSL2R on this. It's not so bad. Yes. Okay. And now, so you also have like generalized Milnor-Wood. Generalized Milnor-Wood, which gives you that this, what, I guess Toledo invariant I want to call T. So this says that T again is like takes values in some closed interval. So it's bounded above and below by some number. Is the Euler characteristic times the rank of the group or something like that, but in some notion of rank. I only care that it's bounded. So it says that this is bounded. So another good question would be, well, what does it mean now when this is maximal? Because for the motivating example, maximal exactly corresponds to the very geometric representations, those that give nice quotients and a hyperbolic metric on the surface you started with. Now, if you have a representation of the fundamental group of a surface into some higher Lie group, like SP6R or something, then what does it mean if this invariant takes its maximum value? So there's a couple things that are known. So there's a paper fairly recent by Berger, Yazzi, and Wienhard, where they study, so this is 2008, where they study these representations, so maximal representations for any surface, closed or open, into these B groups of Hermitian type. So they show that rho is maximal in this sense. So like T of rho takes the maximum value, implies that rho is faithful and discrete. So injective and discrete image. So it looks like a nice representation acting on some space, but we don't really know where it acts. And rho has a notion of a boundary curve. So it admits continuous, equivariant boundary curve. And they don't talk about proper actions in this paper. Some of the maximal representations are in Azov, and then you can know that they act properly by other papers. But those, for example, that have the equivalent of punctures are not in Azov, so you don't get proper actions this way. But I'm going to tell you where they act properly in the next section of the talk. So I'm not going to say more about the equivariant boundary curve. I just wanted to say there's already some results that tell you why you should be interested in this type of representation. Okay.
Usually you get an act on some kind of homogeneous space of G.
Yeah, you can.
Is that what the
That's part of what we do in our paper. Okay. So section 3, SP2NR. So, okay, I told you first what a classical Schottky group was, then I told you what maximal representations were, and then I told you a generalization of maximal representations. So now I'm going to tell you a generalization of Schottky group, which fits with this generalization of maximal.
Cool.
Okay, so what's SP2NR? So if you've fallen asleep in the last couple minutes of this talk because I was saying abstract nonsense, now this is going back to earth very quickly. So this is a group of matrices, 2n by 2n real matrices, such that so omega of AU AV equals omega of UV, where omega is a skew-symmetric, non-degenerate bilinear form. Yes. Probably, yeah.
The standard one.
Maybe if you want. Yeah, there. This sentence goes before this one. Now it's fixed. Also, I mean, I didn't put this inside the set description, so it's fixed. So it's a group of matrices which preserve a form. Usually, you might think of ON or something that preserves a symmetric positive definite bilinear form. This is roughly similar, except vectors have norm 0, which is a bit weird. Because of skew symmetricity, if you pick the same vector twice, right, omega of UU is minus omega of UU. Because skew symmetric means when you switch the entries, you put a minus sign. So it has to be 0. So the norm of every vector is 0 with this type of thing. OK. Now I'm going to tell you about the Lagrangian Grassmannian. Lagrangian Grassmannian is the space lag 2n. Yeah, exactly. So all vector subspaces of R2n, so subspace, such that dimension of V is n, so half the dimension of the vector space, and omega restricted to V cross V is identically 0. So you look at all.
V cross V, just the V.
Well, it's a bilinear.
Oh, you don't think
So-
that's a form. Okay.
Yeah, I could have said restricted to V. I mean, you take two vectors in V and you always get 0. OK, so why do I care about this space? Well, sp2nr is a group that I'm interested in. I want to define Schottky subgroups of this. And this acts on this. Because it acts on R2n. And it acts linearly, so it preserves linear subspaces. And it preserves omega. So if omega was 0 on V, and you act on V by an element of here, it'll still be 0 because of this. OK? Now, so one thing to note is that sp2r is the same as sl2r. That's because the only skew-symmetric, non-degenerate bilinear form on a two-dimensional vector space, by like the first theorem you prove in linear algebra or something, is the determinant. So preserving a skew-symmetric bilinear form is essentially the same as preserving the determinant, up to scaling. So I could pick omega as determinant in the two-dimensional case. So now I have something to generalize from.
It's determinant of what?
Concatenation of the two vectors.
Tensor?
Put them in the first column
Yeah.
of the matrix. So like V comma W becomes like the 2x2 matrix V
Yes.
W. Oh yeah, just so we know. So he used U and V, so you gotta change a variable there.
Column vectors. OK, so now I have something to generalize from because I know what Schottky subgroups in. OK, it's PSL2R, but I could have taken PSP. Doesn't matter because I only care about the action on the subspaces anyway. So I know what Schottky subgroups here are, and so I have something to generalize from. So what's this when n equals 1? So what's lag 2? Well, that's the space of one-dimensional subspaces of a two-dimensional vector space on which omega vanishes. But I said over here that omega on a vector with itself, and actually a vector with any multiple of itself, right? I could pull out k in front and pull it out in front here as well, right? And so it has to be 0 anyway. So in one-dimensional subspaces, it always vanishes. So actually, in dimension 2, this is just RP1, the space of one-dimensional subspaces of R2. And what's RP1? Well, I like to think of this as the boundary of H2, because Well, when PSL2R acts on the upper half plane in CP1, if this is upper half plane in CP1, the boundary of H2 is literally RP1 inside CP1. OK. So RP1 is a circle. So before I was drawing circles, I'll draw circles again, even though here I drew an upper half plane to make Sean happy. So I know what Schottky groups are here. Or rather, I know what they are when they act on the inside. But what if I forget about the inside? What does a Schottky group look like from the point of view of the boundary? Well, my half spaces now are like intervals in RP1. But PSL2R acts on RP1, and I can ask for them to be paired. Like this interval gets stretched everywhere except this, or rather the outside of this interval gets mapped to this one. So it's exactly the same, except instead of having like access to the inside of H2, now I only want to talk about the boundary. But you can do everything with just the boundary. Just have to have a notion of intervals, and a pair of points takes the role of like the geodesics here that we are now blind to. We don't see them anymore. So now we need to generalize this. But we need to know when they are disjoint. So what I want to say is disjointness of half spaces in H2 is determined by the cyclic ordering on RP1. What do I mean by this? If I have 4 points on the boundary, 1, 2, 3, 4, and I link 1 and 2 with a geodesic, and 3 and 4 with a geodesic. If 1, 2, 3, 4 are all oriented in that order counterclockwise around the circle, I am certain that the geodesics are disjoint. But if I do like 1, 3, 2, 4, and link 1 and 2 and 3 and 4 again, they will always intersect somewhere. And similarly, the intervals in the boundary also like overlap.
Do we know that the actions is going to be free on the whole upper half plane, but do we know it's also free like on the boundary?
No, on the boundary it has fixed points.
So like I mean, you can't really determine the subgroup then, because you could have 2 group elements which do the same thing on the boundary.
No, so it acts effectively on the boundary, but not freely.
Okay.
So
it's effective. I used the wrong word.
Yeah.
So I should have just said what I meant.
I think free sometimes means what you said, that like no element acts like the identity except the identity. I think sometimes this is also called free, which is a bit annoying, but so no, yeah, every element except okay, maybe minus the identity but don't worry about minus the identity.
You really want to push it up by the center anyway.
Yeah.
When was that? When did we push it up by the center?
He began the discussion of PSL2.
Yeah. Instead of SL2. But we're never going to use minus the identity anyway, because when we define the group acting here, we have to pair 2 points to 2 points. So you can't land on the identity somehow by asking these points to go there, right?
You really want to do a PSP too, right? Or no?
It doesn't really matter. Like if I wanted to classify components of representations or something, then yes.
Yeah.
But like I'll be choosing some lift of the PSP2n thing when I do this, and it still works out. Okay, so now, yeah, if I only look at the boundary, I can define a Schottky group just by now defining a Schottky group means take a bunch of points, twice as many as I used to have geodesics. So before I needed to choose an even number of geodesics. Now I need to choose a multiple of 4 of points that are all cyclically oriented so that all the geodesics that they define are disjoint. So now I know how to do this using just the boundary. And I am ready to generalize this to Lagrangians in R2n. I just need a notion, an appropriate generalization for cyclic ordering. So how strict am I with the end of the...
Well, if we don't have a program, it actually doesn't matter too much, but I think we do today. So, I mean, you could finish up in like the next 5.
Okay, so I'll have to be super quick,
Maybe
but that's okay.
6.
All right.
Possibly 7. But that's like really.
So the cyclic ordering on the circle is really a property of triples of points. If I have 3 points, 3 ordered points, I can tell whether they're clockwise or counterclockwise. Right? This is counterclockwise and this is clockwise. And any disjoint, like any triple of points where all 3 are different, will either be clockwise or counterclockwise. For example, here 2, 3, 1 is also counterclockwise. So there's an invariant in Lagrangian. So yeah. M of PQR. So this goes from triples of Lagrangians into minus n plus 2, n minus 2 up to n. So it goes into integers where n is this n, so half the dimension of the vector space.
So it'd be like 3 times smaller.
Yeah, thank you. So it takes a triple of Lagrangians, so 3 n-dimensional subspaces here, and gives me a number. So for example, if we take this for Lagrangians in R2, which we said was RP1, this only takes values minus 1 and 1. And it takes value 1 exactly when it's like a triple, which is counterclockwise. And yeah, so I need to say a bit more about this 3, I guess. So so this means pairwise transverse. Triples of Lagrangians. So in RP1, it just means distinct. So if I have 3 distinct points, it's 1 if they're counterclockwise and minus 1 if they're clockwise. So here I have a bunch more values. But I don't want to care about any of them except the minimum and the maximum. So call PQR in Lagrangians cyclically oriented if M of PQR is n. And it turns out that this has enough symmetry properties that it behaves exactly like you would want for a cyclic ordering. So if you reverse the order of the points, it becomes minus n, so it's not cyclically oriented anymore. And if you cyclically permute, like if you do QRP, it'll still be n if it was n before. So it behaves like a cyclic order. Now you can imitate the Schottky construction because you know how to do it from only cyclically oriented points and then find maps that pair them together. So a Schottky group in SP2NR is defined by emulating the PSL2R construction. But now points on the boundary means Lagrangians, and cyclically ordered means this cyclic order. So Maslov index is maximal. So this is called the Maslov index, by the way. Okay. Now, big punchline theorem. Is that Schottky, in this sense, is the same as maximal?
The Toledo maximal?
Yeah. So this was the whole point of the talk. They are the same, and this gives a geometric version of maximality, just like the holonomies of hyperbolic structures does in the 2-dimensional version. It gives more geometricity than just saying we have a bunch of points like in S1. Actually, so if I want to have time to show my pictures, I need to do this now. So SP2NR acts on RP 2n minus 1. And this is where, like, this is where my subgroups, my Schottky groups, will act properly discontinuously. And this is where I want to take quotients, not in the space of Lagrangians. So even though the Lagrangians are what you use to define the group by saying, now I take elements of SP2NR and map some 2 Lagrangians to 2 other Lagrangians that are cyclically oriented, this is not where I want to look at the action, because there it's going to be a bit like on the boundary of H2. It's like the quotient is not that nice. Well, okay, here it's a bunch of disjoint circles, but still. RP2n minus 1 is the right place to look at. And so let's see if I can do this. How do I go to sources, maybe? Video on. Yeah. Okay, let me show you the other picture first. Wait, where's the other picture? Aha. Okay. So anytime you give me 2 Lagrangians in
Pictures of, right?
R2n.
That's what those are pictures of?
No, because these are linear Lagrangians there. It's not linear.
So now we're doing SP4. Okay. So in SP4, SP4R, the RP2n minus 1 that I talked about is RP3. So we can draw pictures because it's 3-dimensional. Now, to a pair of Lagrangians, so in RP1, to a pair of points in RP1, I can associate a geodesic in H2. Now, the point is, to a pair of transverse Lagrangians in R4, I can associate a surface, a hypersurface in RP3. This is what the hypersurface is. So each of those 2 tubes, I mean, they're hyperboloids. Each of those 2 hyperboloids is defined by a pair of Lagrangians. So I have 4 Lagrangians, just like with 4 points in the boundary, I get 2 geodesics. With 4 Lagrangians, I get 2 hyperboloids. And if the 4 are clockwise or counterclockwise, then they are disjoint. And if they were like not cyclically oriented, they would intersect. They would have some intersection. And so if you take more pairs of points, you get more hyperboloids. And this is what the other picture is. Okay. So what is this picture? This is the equivalent of one of the first things that I drew. So the H2 picture for this is taking 4 geodesics, taking elements that identify them like this, and looking at like their first layer of images inside each bubble. So inside each bubble, you get 3 more bubbles. Here, it'll be inside each hyperboloid, you get 3 more hyperboloids. So the biggest hyperboloids, so like the defining ones, are the red ones. So there's an element of SP4R sending the big red hyperboloid to the slightly smaller red hyperboloid, and another one sending this blue hyperboloid to this blue hyperboloid. And when you apply those and their inverses to the hyperboloids, you get the orange and the green. So the top is the easiest to interpret, maybe. When I send this red hyperboloid to this red hyperboloid, I send the big red one, this red one to the orange, and this blue one to this green, and this blue one to the other green. And similarly, the other green things are images of the blue, and the orange things are images of the red. This is something I want to 3D print.
Yeah, we should do it.
No, I don't. but I'll come up with one and I'll send it to you.
Stand next to the thing.
I already have a picture of basically this taken by Virginie on Facebook.
I know. Say hi. Okay, cool. No, that's not for Facebook. It's for...
All right, thanks for listening.
Oh yeah, thank you. Given time, maybe well, we already asked a lot of questions. Are there any questions? Oh, we should keep it short. Nope. Okay, great. Well, let's thank JP again. Yeah, and if you need my autograph, let's go ahead and do that quickly. There's one. Make sure everything's written on it. Right there. And then I need your autograph for my talk. Oh. Forgot to give me the sign on your talk. Okay.
Thank you.
Okay. Anything else? Nope. No.